In this series of videos I'm going to introduce analytical mechanics for chemistry. So, as a physical chemist you don't really need a big knowledge about analytical mechanics. But it can be useful because many or almost any physical system you're going to study in the rest of your career as a physical chemist will in the end use tools that are derived from analytical mechanics. You will very often have to deal with the quantum version of the system, but of course, having seen at least once in your lifetime the classical system, the classical equivalent, will simplify your life for quite a bit. Now, as it is only an introduction, and as having all a very deep knowledge about analytical mechanics isn't important as a physical chemist, I will cut a huge part of the theory, of the math, and of the physics. I'm also a physical chemist, so I don't have all this incredible knowledge that a theoretical physicist could have. So, a big part of the material I used are the Landau Lifschitz Mechanics book. You will actually see that it's very similar to this series of videos. Of course, if you're interested in having a more in-depth knowledge about the method and about the theory, you can go and check out for the book. Another interesting book that gives a little more information about the mathematics and guides you a little bit more step by step, but I did like a little less, is Hand and Finch, Analytical Mechanics. But now, analytical mechanics is simply a different way of talking about classical Newtonian mechanics. We know that classical Newtonian mechanics is able to explain how every single thing in the universe, not in the universe, in our day-to-day life, so in a classical situation, works. We can, if we know the forces, we can predict what will happen, etc, etc, etc. It works. But in some situations, for example, complex systems with many degrees of freedom without friction, it can be quite complicated to use vectorial quantities like forces, as you do in Newtonian mechanics. So different scientists have developed different formalisms that can be used to simplify a certain kind of problems. The most important ones are the Lagrangian, the Hamiltonian, and the Hamilton-Jacobi, or better, at least the most famous ones. I will give a little introduction to all three of them. Hamilton-Jacobi will only be really a few minutes, and show some use cases that are quite similar to what you will then go and see in, for example, a quantum chemistry course or a statistical thermodynamic course.